Emina. I'm very excited to be here. Thank you so much for inviting me. I am a senior principal of data scientist at Amazon Web Services and affiliate faculty at the University of Washington. At AWS.
Emina, can you use the hand? Yeah.
You can hear me? Can you hear me now? Better? Okay. Great. All right. So at AWS, I lead the design and development of a new programming language called Cedar. So what I'm going to do in this lecture is I'm going to talk about how and why we designed Cedar and how we built it using programming languages and automated reasoning, which is industry speak for all the methods, techniques. Basically the idea is to show you guys how we use all the cool stuff that you've been learning about in the summer school in real life to make languages that are expressive, fast, safe, and analyzable. And we'll hear in the rest of the lecture what all of these words mean. But the first thing that we're going to talk about is, well, what is authorization? Authorization is the problem that every multi-user system has to solve. So basically, every web app, every website that you've ever used has had to solve this problem. It is the problem of determining who can perform what action on a resource in an application. So for example, if you have an online banking app, that banking app has to decide which accounts you are allowed to access. Same for online health, as well as things that are less critical, like photo sharing. All of these applications that you use every day, Netflix, streaming, everything, they are solving billions of authorization problems an hour. Okay, so that's what authorization is. It is something that has to decide whether you, as a user, are allowed to perform a certain action, view a photo, delete a photo, update a photo on a given resource. Now, this sounds like a really boring old problem, right? Hasn't been solved, and in some sense it has. The theory of how to build authorization systems is well known, and you can pick among many well-established authorization models. For example, you can give access to resources to users based on their role within your organization. A manager is allowed to see their employees' record, so that's role-based access control. You can give access based on the properties or attributes of your principals or resources. For example, I'm allowed to access all Amazon lockers that are within the same zip code that I'm in, okay? Or a more recent development that came from some research from Google is relation-based access control, where you're giving access to resources based on relations between the principal and the resource. For example, this comes up in things like Google Docs. I'm allowed to view a resource on which I'm a viewer or an editor. So there's a viewer or editor relation from principal to resources, and based on the tuples in that relation, you decide who's allowed to have access. Okay, so this all sounds pretty simple, right? But actually implementing one of these access control models within your application at scale at which web applications work turns out to be very, very hard. It's hard to author these policies, it's hard to audit them, and it's hard to maintain them. To see why, let's start with a simple example, and we're going to be using this example throughout the talk. There's this hypothetical, actually it's not hypothetical, we built it, but there's a tool application called TinyTodo, which allows users and teams, so see we have a bunch of users here, we're organizing to teams, so it allows users and teams to create, manage, and share to-do lists. Okay, so here's an example list 1, 2, 3 that these people that we have on our screen, our users, are going to be doing stuff with. Now, if you were going to build this as a web app, what would happen is you would have some front-end code, some JavaScript that's presenting a UI to the user, and then the user clicks a button, an API call is made onto a backend, which is going to lots of cases going to be some Python piece of code running, right? So if a user clicks a button and says, show me the contents of this list, then this backend has to decide whether that particular user is actually allowed to see the contents of that list. The way in which this has been implemented in the past looks something like this, okay? So this is the code, this is the backend code that gets called, okay? It's some Python method that takes as input a request. is going to unpack that request, it's going to do some checks, and if those checks pass, it's going to give you the contents of the list. Now, I'm going to let you stare at this code for about 30 seconds, and I'm going to ask somebody to tell me, what is this thing actually trying to enforce? What are the access rules that this thing is attempting to enforce in Python here? Who is allowed to do what? Any takers? Yes?
The user must be either the owner or an operator access
Or an admin?
yes.
Yes. So, exactly. So you're looking at this code, and it's really hard to see what's going on. It's a really simple piece of code, and even a bunch of really smart computer scientists in the room, it probably took you about 30 seconds to figure out what's going on, especially since this code is checking the negation of what you want to enforce, right? It checks the negation of what you want to be true, and then fails, and if it doesn't fail, then it follows through to actually give you the contents of the list. Now, this is really hard to write down, right? It's hard to get this negation and nested if the nested conditional logic correct, as pretty much every year when this list of CVEs, like really bad security errors, comes up when it's published, getting these branching things incorrect is one of the top items on that list. So this is really hard to author. The second problem is that this is really hard to audit, okay? Imagine that you have to convince an external auditor, which many companies do, that your code satisfies certain access invariants, right? Like, private buckets are not linked. The information in private buckets is not linked to the public. How do you prove that? Well, you have to examine the application code. So this is the analysis of general purpose code, which is very hard, especially for code for which there aren't that many tools to analyze them, like Python. This is really hard to audit as well. And then the final problem with this approach is that it's also hard to maintain. My app is going to have a bunch of actions, right? Getting the contents of the list is just one action. You're going to have to do things like create lists, check off the items in the list, add items to the list, share lists with other people. So all of those is going to amount to one of those API calls. And you're going to have to repeat this logic in each one of them, okay? And if you want to change your authorization logic, you have to change and redeploy your application. So getting this right is quite hard. An alternative approach to embedding your authorization logic within your application is to use a dedicated authorization engine. So in this case, your actual application code never changes. All you need to do is insert that line at the beginning of the method that calls an authorization engine. The engine evaluates your authorization policies, and if the answer is allowed, you proceed. If the answer is denied, you bail. Okay? So here is what authorization policies might look like, and this is your first look at Cedar. So this is a bunch of Cedar policies that are implementing those same rules in Python that you just saw. Now, you've never seen Cedar before, but it should be much easier to see what's going on here, right? There's rule number one. It says that every principal is allowed to perform every action on any resource if they are the owner of that resource, okay? That's what the first rule says. The second rule says admins can do whatever they want. Fair enough, right? They're admins, and that's exactly what that code was trying to do in Python. And then the final one that we have here says that the principal is allowed to perform the get list action, to see the contents of the list, if they are in the readers or editors relation with this resource. Okay, they're either in the readers or the editors team for that particular resource. Okay, so that's your quick taste of Cedar. So what is Cedar? It is a relatively new authorization language. I keep on calling it new, right? But it's been out for 2 or 3 years now, so getting old. It is used extensively at AWS and at companies that you're probably familiar with outside. So some examples include MongoDB, Cloudflare, Cloudinary, and so on. Everything that I talk about today is open source. So you can download Cedar, you can play with it, you can look at our proofs, and we're going to get to that later. So exactly what it is that we built and exactly what it is that we proved. So what's special about Cedar? Why did we bother building a new authorization language? There are actually quite a few authorization languages out there that you could have used and picked up before Cedar. So the question is, why did we build another one? Does the, besides the fact that it's fun to build new languages, I'll admit to having a fun designing it. But the primary reason was that we wanted to find a new balance between the 5 design criteria that we identified as important to authorization users, so basically developers who need to build these systems, when they are building their authorization models for their application. So the first one is expressiveness. Your authorization language should be expressive enough to capture all the authorization access control models that can be used in practice. So that would include role-based access control, attribute-based access control, and relation-based access control. Okay, so it has to be expressive enough to cover all of those. Otherwise, it's still useful, but you're going to miss a lot of use cases. Okay, and not many people are going to be able to use it. The second one is ergonomics, right? So it should be possible for people who are not programming languages experts to read and understand the policies in your language and even to write them. Because people who write Cedar policies are not just programmers. There are several different personas who write these policies, but an obvious one is sysadmins, right? So they are not necessarily going to be experts in programming languages, and they should be able to understand those policies as well. The third one is performance. So authorization systems run billions of times an hour in really large-scale applications. That is a lot of calls. So this evaluating authorization policy, actually a set of policies, has to be really fast and it has to be predictable. You should be able to put hard performance bounds on how long it's going to take, how many resources you're going to spend while making an authorization decision. The next one is safety. So your language should be type safe, right? You should be able to statically catch and rule out common authoring errors, right? So somebody trying to add together a string and a number. In some languages that's okay, in Cedar that's not okay. The final criterion, and this is the one that is unique to Cedar, so we balanced all the other ones to achieve this last one, we call analyzability. What that really means is that Cedar is carefully designed so that it has a sound and complete reduction to a decidable fragment of SMT logic, which means that we can fully automatically prove that your set of policies satisfies access invariants that you care about. So this last one is the most important one. That's the line that we don't cross. Even if there's a super useful feature that involves some sort of a loop that somebody wants, we're not going to add it to the language. If you lose decidability, it does not get added. Okay? So the other thing that's interesting about Cedar is that it is the first authorization language that has been built using automated reasoning and formal methods, and we're going to see what that means in this talk. But essentially, we use this process called verification guided development to build every component of Cedar, from the authorizer to the type checker to this symbolic compiler, which reduces Cedar policies to SMT. We build each of those things twice, once in Lean and once in Rust. We prove all the meta theory in Lean, and do people know what Lean is? Yes. So it is a interactive theorem prover similar to Rust. It's based on independent type theory. So we prove all the meta theory in Lean, and we use differential testing to check that our Rust implementation matches the Lean design. So Lean is our formal specification, our model, it's fully executable, it's verified, and we check that the Rust code matches the Lean code using differential testing. Okay. So I'm going to go over some of the design and development highlights, sort of the interesting programming languages, formal methods and things that we have done while developing Cedar, starting with the language design. Okay, so here's a Cedar policy again. so you've already seen one of those things. And the syntax of Cedar policies is simple and uniform. They consist of three parts. The first one is the effect of the policy, which is to either permit or forbid access. Okay, so permit gives you explicit permission to do something, and forbid explicitly forbids you from doing something. The next part is called the policy scope. And in the policy scope, you can optionally constrain the policy variables. So these are the variables inputs to the policy, principal, action, resource, using either equality or this in operator. So you can intuitively guess what in means, and we're going to go into it. We're going to explain it in more detail later. But it is essentially checking membership in that hierarchy that we've seen at the beginning. Like it's checking whether a user is a member of a given team. The final part of the policy, you can have as many of these clauses as you want, which are also optional, are these when or unless clauses, which further constrain access by letting you write these expressions, and I'll tell you later what's in the expression language, but letting you write these expressions over the attributes of any of these variables. Now, the principal, action, and resource are all entities. So what is an entity? You can think of it as a pointer. It's a reference to a stored object, and entities can be organized into an entity hierarchy. This entity hierarchy, and this part is important, is not an arbitrary graph. It has to be a DAG, okay? So there are no cycles. Why not? Because in real life, when you put people into hierarchies, there are no cycles in hierarchies. You know, when you're putting files into folders themselves are not cyclic, and so on. So that is the data model constraint for the Cedar data model. These store objects, you can put them into these DAGs, which we call the entity hierarchy. Now, in addition to being able to put them into these DAGs, you can also attach attributes to objects, and you can think of that as each of these named references has a map attached to it, or a record rather, where the fields are named and their type, and the kinds of values that can go into the field, and this is the interesting part, the fields themselves can be pointers to other references, okay? So a valid Cedar value is either a record, an entity, integer, string, Boolean, set of those things. And a bunch of other types that we're not going to go into great detail with, but which are very useful in practice, like things to deal, types to deal with IP addresses, to deal with date times, and so on. Okay. So this is the Cedar data model. We are going to be evaluating policies against an entity store, which is the thing that stores the entities, the hierarchies, and the attributes. The request is what you pass to Cedar in addition to your entity store, and it's an environment that binds your free variables to appropriate values. So there are actually 4 variables. This context variable, which I'm not using in the policy, and I'm not going to show you anymore, but that one is a record rather than an entity, and within that, you pass to Cedar information that is transient. Okay, you don't want to store everything in the database, right? The only things that store in the database are the things that are permanent, but transient information that's also useful, like the source IP address from which the request was made, the current time of day, you can write policies against that as well, and you would have that information as part of the context. But the principal action resource are all going to be these entities, named entity references that are going to be pointing to something in your entity store. Now, given a request and some entities, to evaluate the policies, Cedar implemented an algorithm that amounts to these 2 rules. The first rule says that a request is allowed when it satisfies at least one permit policy. But it is denied if it satisfies a forbid policy, okay? So you have to satisfy at least one permit policy and no forbid policies in order to be allowed. So let's see what that means on an example. So here's our example policy and our example request. According to these 2 rules, do you think that this request is allowed? Is Kesha allowed to perform the get list action on this list 1, 2, 3? Yes.
Yes, because temp readers fall into temp is the readers and Kesha is a temp.
Yes, that's absolutely right. So this permit policy gives her explicit access to perform this action because she is a member of the temp team, and the temp team is the team of allowed readers for list 1, 2, 3, and the policy says if you're a reader for that resource, you're allowed to see it. Okay, so let's see a slightly different one. So watch what changes in my request. The only thing I'm going to do is I'm going to swap out Kesha with Emma. What happens now? Is she allowed to see it? According to my 2 rules? No, exactly. She's not allowed to see it because we only have one permit policy in our system. And this permit policy doesn't fire, okay? Because she's neither a reader nor a writer of this resource, and access is denied. So Cedar is, in authorization parlance, a default denial language, meaning if there is no policy that talks about this request, the request is denied. All right, one final example of the semantics. Oh, and here I added a new policy action user access. All right, one final example. I've now made the policy a little bit more interesting. We also have a forbid policy now, and we're asking whether Andrew is allowed to perform the create list action on the application time to do. Okay, so now the resource is the entire application, not an individual list. Is he allowed to perform this action? No. Why not?
No, because he's on the forbid list.
Because he's on the forbid list, yes. So the permit policy will fire. So this permit would say, yeah, sure, you can access it. But the forbid also fires. And as soon as the forbid fires, the forbid overrides permit. And that's something that's proven about our authorization algorithm. Access is denied. So this is called an explicit denial. Now, why did we design the language to look like this, right? Why did I pick those operators? Why did I give it that syntax? Why did I give it that data model? Well, it goes back to one of the design constraints, right? The language is designed to enable you to express all 3 of those authorization models that people want to build inside of their applications. So role-based access control, attributes-based access control, and by combining the 2, and we'll see shortly what that means, we get relation-based access control. So let's start with the role-based access control. What these 2 policies are doing is they are giving or taking away access to a principal based on which team they belong in. Okay, so in this case, we are using the role of the principal to give or deny access. To do that, we are using this, and this is probably the most important operator here. We're using this in operator, which is testing graph reachability. Okay? So the in operator is true if there is a path from the left-hand side of the operator to the right-hand side operator in the graph. Okay? So this node Aaron, this entity Aaron is in the temp team, even though there is no direct connection, there is a path between the 2. Okay? So the in expression evaluates the 2 if there is a path in the entity hierarchy in this DAG from the node on the left-hand side to the node on the right-hand side. Okay? Everybody good with in? So we use the hierarchy to model roles. And roles can be nested, right? So you can have interns nested in admins, and that way we get a nice sensitivity property that you might want to express when you're doing relation-based access control. Now, you might remember me saying that we wanted to ensure that Cedar had good performance, right? And now I'm telling you I have an operator that has graph reachability in the language, right? On the fly. So clearly something is wrong with those 2 statements. They can't both be true at the same time. So how do we actually make this work? How do we implement this in operator efficiently in Cedar? In fact, in Cedar, this operator is constant time. And the way that we do it is we don't define the semantics directly on the DAG. What we do is we define the semantics of the language, and implementation works that way too, on the transitive closure of this DAG. So what you're actually passing to Cedar in code is not the DAG itself. You basically pass it a map that looks like this. It takes the entity name, it gives me the attributes of that entity, so it's going to be one of these record things, and then it gives me the full ancestor set, the transitive closure of that DAG. In this case for Aaron, the transitive closure includes the team interns and the team temp. So that means that at runtime, we can test whether you're a member of one of these teams simply by performing a membership check in this set. So why did we do things that way? I mean, clearly it makes our life easier, right? We can just test this in constant time. But there is a real practical reason why we did that. And the reason is we don't know for a given application whether it is easier for them to calculate this transitive closure on the fly, whether that is cheaper to calculate it and cache it, or to maintain the transitive closure incrementally on the disk. Okay? So this way, the Cedar semantics gives the application the choice how and when to compute this transitive closure when a request is made, and what is most efficient for the data access patterns and for the layout. Okay? So the semantics of the language, even though the data model, so that we can visualize it and talk about it and explain to people what it means, we always show this graph. The actual semantics is defined on the transitive closure of this graph, and what the evaluator gets is this map, which maps the entities to their attributes and to the full ancestor set. So that's the magic in operator, and that's how we do role-based control is here. Now, to do attributes-based control, you're going to use these conditions. So the conditions let you access the attributes of a resource, and you can also use the in-operator in the condition as well. There's no constraint there. Now, the thing that's interesting about these conditions is this has operator, and the has operator is essentially letting us introduce, in a lightweight way, option types into Cedar. So you can declare in your schema, so that's what we call the type declarations for a Cedar policy. In your schema, you can declare a field or an attribute to be optional. But the type checker will not let you dereference an optional attribute before checking that you have before checking that the attribute actually exists. And we'll talk about that later on. The type checker is smart enough, it's actually flow sensitive. It knows whether you have checked for the presence of this attribute or not. So once you have checked for its presence, you're allowed to dereference it. So you can say things like, the owner of the resource is the principal. That's when you're allowed to do it. What can go into this expression language? So what it actually consists of? Well, there are no loops and there are no side effects. So it's loop-free expressions, pure. It has these operators in equality, of course, set membership conditionals, Boolean operators, limited wildcard matching, and a bunch of other extension types.
What is wildcard matching in this context?
In this context, it's very, very simple. And the reason why we keep it very simple is so that you can translate it to efficiently decide the S&P formula. But it's basically, you can have, the operator is called like, and you can write, principal.name, like, star, Emina. And the only wildcard that we allow in the pattern has to be concrete, is the star. So it's globbing, basically globbing operator. Now, all of these operators are carefully chosen so that we can perform this reduction of S&P and so that we can bound worst case running time of any Cedar policy set against the input. And if you're not using set operators, your worst case running time is actually going to be linear in input size. And if you use our worst case operators, so like set complement, set subset, and so on, is going to be worst case cubic, which is still not bad because normally what you do is you don't pass your entire entity store, not the entire database to Cedar. We actually give you methods that let you select soundly a subset of the stored data that is sufficient to correctly evaluate the policy. So you're going to be evaluated against what we call a slice of the entity set. Now, by combining the hierarchies and the attributes, you can express relation-based access control. Now, there are authorization languages in which relations are native concepts, and actually that's the only thing that you can talk about, just relations. You can't really talk about attributes, you can't have attributes with strings and so on. You only have relations. Think of it as a layer on top of SQL. In Cedar, you can express these relational patterns of control without having to have a native concept of relation. And the reason is that you can actually have an entity represent a set of other things, okay? So here to express the reader relation, I'm going to put an attribute called readers on the resource, and I'm going to give the type, I'm going to make the type of this attribute a team, and a team represents a set via this in operator, okay? So not only can I represent relation, I can actually represent transitive relational containment using this trick. So that's how you get relation-based access control in addition to role-based and attribute-based access control in Cedar. Okay, so popping a step up, if you take a look at one of these example policies, what can you tell me about, the kind of things that I can write in the conditions versus the kind of things that I can write in the scope?
You can have like a Boolean and in the permits.
Mm-hmm. You can have, the condition contains a superset of things that you can write in the scope.
Oh.
So anything that appears in the scope is very limited, okay? You can only write equality and in, and you can write those two things in the condition as well. So you might be wondering, well, why bother with the scope, right? What's the point? Why did we design the syntax this way to make a distinction between the scope and the conditions?
Because maybe it lets you assume during the conditions that the scope is a certain way, which might make it easier to analyze.
Very close. It serves several purposes, and one of them is type checking. So it actually, type checking does exactly that. So an alternative is, one of them is very simple purpose, which is readability, right? So here's a hypothetical syntax for Cedar where we don't distinguish between the two. This is really hard to read, right? Like you have, as a human being, you have to manually parse this thing in your head to decide that, oh, this is actually doing role-based constraint followed by an attribute-based constraint. So they're interleaved in a way that's kind of hard to read. So that was number one. This is the ergonomics readability. That's how you do this code. Number two is that it also allows us to make Cedar run really, really fast using